So in this video, we're going to discuss a formula called the z-score. And the idea behind this is that we want to convert data values into this score instead. So it's kind of like, my weight on a scale is measured in pounds. If I went to Europe, it'd be measured in kilograms. We could also describe my weight in terms of a z-score. What's nice about a z-score is it doesn't have any units. When you do this calculation, the units cancel out, and so it's a unit-free measurement. And that means we can just look at a single number which is going to represent the data. Now, why would you want to do that? Why would I care what the z-score is for my weight, for example? Well, I might want to know if my weight is unusual, for example. So I would go and get my weight on a scale and get the measurement of it. I'd go look online to see, or somewhere, look it up to find out what the average weight for men at my height is, And then at that point, I would plug that information into the formula. I'd have to have some estimate of the standard deviation. That can either be estimated from data or found somewhere, if somebody has done that for us already. And then at that point, I can calculate a z-score for my weight. And once I've done that, I'll know at that point whether or not my weight is unusual. And the way we're going to do that is once we calculate this number, we're going to compare it to the scale above here that I've written on the board. So generally what we're going to look at is that, if the z-score turns out to be anything from -2 to 2, we'll say that those are typical or ordinary z-score values, indicating that this data point that you converted into a z-score is ordinary or typical. The 0 represents the scenario where you're average, exactly average. Let's look at what this calculation does. It finds the distance between your value and the mean. It finds out how far apart they are. And then it expresses that distance in terms of standard deviations. So actually, this is a lot like the K we saw in Chebyshev's theorem or the empirical rule. It says the number of standard deviations away from the mean. So it's the number of standard deviations away from the mean. So when I have 0 means there's no deviation from the mean. We're exactly at the average value. If you subtracted the two numbers and this one was the average, mean minus mean would give you 0. That's a scenario where you're completely average. If you have a z-score of 1, it means you're above average, right? A z-score of 2, above average, but still within the ordinary range. Of course, you can have any decimal in between those numbers. But what happens when you start to get z-scores of, 2.6, 2.7, 3, 4, 5, so on and so forth? Now we're talking about you're in the unusual range. If you come down below, again, -1 is below average, -2 is below average, -3 and 4, we start to get into the area where we're unusually below average. Why are we using that cutoff? Well, we learned 2 rules that helped us interpret data distributions. Let's talk about the most general of those, Chebyshev's theorem. In Chebyshev's theorem, if you were 2 standard deviations away from the mean, at least 75% of the data was within this span then. At least 75%. So no less than 3/4 of the population exist in this span. So you may say, well, I wouldn't define, being in a group that's only comprises 25% of the population as being necessarily unusual. Well, that's probably true. And so that's why, this is not hard and fast. The way I've drawn it, it looks kind of, as soon as you cross over after 2, it's unusual. Actually, this should kind of gradually fade into unusual. The further you go out, you start to get more and more unusual. If you have a z-score of 10, that's unusual. Under any stretch of the imagination, that's unusual. On a bell curve, though, remember, this same span from -2 to 2 captures 95% of the population. And now I think you could truly say that getting into this area would definitely be considered unusual. It's pretty rare to be above 2 standard deviations on a bell curve. It's very hard for us to do that in our everyday lives. For example, my height is not unusual. My IQ is probably not unusual. My weight is not unusual, so on and so forth. All right. So again, the purpose of this calculation is to be able to determine if values are unusual or ordinary. Once you do the calculation, you strip away all the units and you're able to just know something about the data point immediately just by looking at it. For example, I don't know anything about the weight of, say, Indian elephants. I don't know anything about it, but if I was looking at a picture of an Indian elephant and somebody had calculated the z-score and told me, the z-score for that Indian elephant's weight is a 6, you would know right away that's an unusually large Indian elephant. If somebody said the weight for that elephant is a -1, you'd say, well, that's slightly below average and not unusual. Very nice thing to be able to do. No matter what we know about the data, by knowing the z-score, we know if something is ordinary or unusual. Another use for this is to make comparisons between scores. For example, if I have a student in one class earning a certain grade in a Stats 1 class and have a student in a different class earning a certain grade, how do we compare their scores? It's probably a better idea to use a z-score to compare their scores than to just look at their raw scores and compare them. Because we know that for different classes, we have different average grades and different standard deviations for grades. And making a comparison that's more fair involves using something like the z-score to compare the relative position. Everyone knows that experience of being in college and having one professor who fails almost all their students. If a person takes that class and ends up with an A, that's a really impressive A. If somebody takes another class with a more traditional professor who doesn't fail most of his students, getting an A in that class doesn't seem as impressive as getting an A in the first guy's class. So that's why it's probably better to compare grades based on something like a z-score comparison than to look at them just from a raw, I got an A, you got an A, we had the same grade. If you take a different class, it really isn't necessarily the same experience, the same difficulty to get that grade. So 2 uses mainly in the beginning of the course for z-scores. We're going to use it to describe whether something is unusual or ordinary, and the other use is going to be to compare different values from different places and see if one value is truly higher than the other.